Alright, in this video I'm going to demonstrate how to find the residues of complex functions at singularities. So I've got a few examples here. In the previous video we presented the formulas for working these out, and here is the summary of the formulas here. So in the first example, this function is going to be singular when the denominator is equal to 0, so z squared minus 4z plus 5 equal to 0. Well, this is going to be equal to 0 if we use the quadratic formula when z equals to 4 plus or minus the square root of 4 squared minus 4 times 5. 4 squared is 16. 4 times 5 is 20. So this is 4 plus or minus square root 4. So this is 4 plus or minus 2i all over 2. So this is going to be 2 plus or minus I. So, and these are going to be simple poles. So these are going to be simple poles. So if the simple poles, we can actually use this formula number 3 here. So we're just going to differentiate the denominator and then plug in the singular point. So if you start with 2 plus I, the derivative of the denominator is going to be 2z minus 4. Then we plug in z is 2 plus I here. So the numerator is going to be 2 plus I. Denominator is going to be 2 into 2 plus I minus 4. So 2 plus I here, 4 plus 2I minus 4. The 4 cancels out in the denominator. So got 2 plus I all over 2I. So this is 2 over 2I plus I over 2I. So the first one is just going to be minus I, because 1 over I is minus I. The second one is going to be 1/2. So that's going to be the residue at z equals to 2 plus I. And then the residue at 2 minus I, which is the complex conjugate of 2 plus I, in a similar manner, it's going to be, so here we plug in 2 minus I this time. So 2 minus I in the numerator, 2 into 2 minus I minus 4. So 2 minus I all over 4 minus 2I minus 4. So this time we got 2 minus I over negative 2I. So this is going to be 2 over negative 2I plus I over 2I. It's going to be 1/2 plus I. So that's going to be the residue at the point 2 minus I. So that's that for part A. We're now going to go to part B. So in part B, got z minus 1 over z squared into z squared plus 1. So part B, f of z minus 1 divided by z squared into z squared plus 1. There are going to be two singularities for this one. Namely, it's going to be 0, and 0 is going to be a double pole. So this is simply because 0 is a double root of the denominator. So whenever your singularity is a double root, the denominator, then it's going to be a double pole. Whenever it's a simple root, then it's going to be a simple pole. So plus or minus I, these ones are simple poles. So if we start with the z equals to 0, so the residue of f of z at z equals to 0. So since this one is a double pole, we're going to be using this first formula here. Every m is going to be replaced by 2. And so what we're going to have here is the limit as z goes to 0 of the derivative of z minus 0 squared, which is just z squared, and then times f of z. F of z is z minus 1 all over z squared into z squared plus 1. And then this is going to cancel out. So we just have the limit as z goes to 0. Z goes to 0 of the derivative of z minus 1 over z squared plus 1. Okay, so to work out this derivative, we're going to, of course, use the quotient rule. So this is going to give us, if we differentiate the z minus 1 and then multiply into the denominator, it's going to give us that. Then if we differentiate the denominator, we get 2z, multiply that with the numerator. And then in the numerator, we're going to get z squared plus 1 all squared. Notice that we are not going to necessarily have to simplify this. At this point, we can just simply plug in z equals to 0. So that's going to be 0. This whole term is going to be 0. So only 1 is going to remain. Plug in z is 0 in the denominator. That's going to be 1 as well. So that tells us that the singularity is going to be 1. Then now we go to the residue of f of z at z equal to I. So there's I and then there's negative I. So since this one is a simple pole, it's going to help us to use the formula number 3. I'm just going to remove brackets here. Z to the power 4 z squared. So then we simply differentiate the denominator and then plug in z equals to I. So numerator is z minus 1, derivative of z to the power 4, going to be 4z cubed, derivative of z squared is 2z. We plug in z equals to I. So this is going to be I minus 1, going to be 4 I cubed plus 2i. I cubed is negative I, so it's 4i plus 2i. So this is I minus 1 all over negative 2i. So this is going to be I over negative 2i plus 1 over 2i. So the first one is going to be minus 1/2. The second one is going to be minus I over 2. So we can actually write this as 1/2 into 1 plus I. Then we're going to have to do a similar computation for z equals to negative I now. So this is going to be z minus 1, 4z cubed plus 2z. So plug in negative I this time. Going to be minus I minus 1. 4 into negative I cubed, 2 times negative I. Now negative I cubed is so let's just work it out here so that you can be, so negative I, negative I, negative I. So the negatives are going to give us a negative. There's 3 of them. Then we've got I cubed, but I cubed is negative I, so this is just going to be I. So this is going to be negative I minus 1 all over 2I. So this is going to be negative I over 2I minus 1 over 2I. The first one is going to be negative half. Second one is going to be plus I over 2. So this time we're going to have 1/2 into I minus 1. Okay, and then the third one, C, we have got f of z is equal to cotangent pi z. Now, of course, cotangent is cosine over sine. So cosine pi z here over sine pi z. This is going to be singular whenever sine pi z equals to 0. Sine pi z is equal to 0 whenever pi z is equals to pi n, where n is an integer. So that tells us that the singularities are going to be at z equal to n. And we know that these are simple roots. So that means these are going to be simple roots of sine. So these are going to be simple poles. So we can use that formula. So residue as z equals to n. So we're going to have to differentiate this. So cosine pi z, derivative of that, it's going to be pi cosine pi z. Now this cancels out. So actually this does not depend on z. So the residue is simply going to be 1 over pi. All right. So at this point, we are going to give you a chance to have a go at DE and DE and F. You can just pause the video, and then when you continue the video, you can compare with our solutions. Okay, we are now going to scroll down to our solutions for D, E, and F. While we do that, we'd like to thank you for visiting our channel and watching this video. We do hope that the video is useful to you, and at the same time, we'd like to implore you to, of course, subscribe to our channel to support the work we do, so that we can produce many more like this. If you've got any questions, comments, you are free to post them in the comment section. All right, so this one is going to be singular when z squared plus 9 is equals to 0. This is going to be give us z is plus or minus 3i. Both of them are simple poles, so we're going to use the third formula. So if we differentiate the denominator and plug in 3i, then e to the 3i pi on 2 is negative I, so it's going to work out to negative 1 on 6. Then for negative 3i, e to the negative 3i on pi is I. Again, it works out to negative 1 on 6. This time we have got two singularities. First of all, z equals to 1 is a simple pole, and z equals to negative I is a double pole. So this one, well, we're not going to use the third formula this time. So we just plug into the second formula, which is this one here, and simplify. So the z minus 1 is going to cancel out, and then we just plug in 1 here. So it's going to be I minus 1. 1 plus I squared is just 2I, which simplifies to that. And then a negative I is a double root. So again, we go through this, then we differentiate this using the quotient rule. Then we plug in negative I, just a few steps of algebra, and it works out to that. The last one is going to be singular when cosine z is 0. This what happens when you have got odd multiples of pi on 2, which are given by n plus half pi, where n is an integer. So if we differentiate the denominator and then plug in, so it's going to be n plus half pi, sine of n plus half pi. Well, sine of n plus half pi is the same as cosine n pi, which is negative 1 to the power n. So the residue is going to be given by that. Okay, thank you.